Yes. Yeah, thanks, Fabian, for nice introduction. And it's my pleasure having with you guys, brothers and sisters. And it's my pleasure to have some of my friends are from Indonesia, and we have a great science working together. Before starting my presentation, I mean, what you saw here, I need you guys to just imagine, I mean, what's the size you saw here? I will be talking about advanced nanomaterials, where every atom counts. I'm working now as a petroleum scientist in Saudi Aramco. When we're talking about nanomaterials, we are not talking about nanoparticles with a very lots of atoms. We precisely talking about nanocluster, which is starting from 1 nanometer, starting from 1 atoms to 100 atoms. It's very advanced nanomaterials. And the objective behind this nanocluster is we're using for production of the clean energy. We use it as a catalyst. We enhance the catalytic activity for it by actually deposit them on metal oxide. And we converging the water actually by water splitting to hydrogen and the CO2 emission to a methanol. The current renewable energy, it has a lots of issues and challenges about the storage of the energy, either the solar cell or the wind itself. But this kind of gas, by using this kind of catalyst, we can store it as a gas and we can have it in day and night. Then why we use a cluster? We have already industrial catalyst, and this is industrial catalyst. It's existing now. But the problem with this industrial catalyst is huge of wasting of materials, and you don't know what's the catalytic active area of this catalyst. And that's why we're changing to actually using the nanocluster and the precise nanocluster. And we support them on the metal oxide to increase the catalytic activity of this one. And it's have been approval in the literature. It's depending on the number of the atoms inside the nanocluster can have and relate to a different catalytic activities. Like gold 9 is different than gold 8 and different than gold 11. But the previous literature review, they use it in the gas phase, while to reach the demand of the industrial catalyst, we need to synthesize them chemically. And this is the difference between what has been reported in the literature in the gas phase and what we produce here. It's a catalytic activities for the cluster as chemically synthesized. And to have this cluster as stable as much as we can, we have to protect this with the ligands. And these ligands around the cluster, it's actually for stabilizing the gold core. But once we need to do the catalytic reaction, we need to remove the ligands to have the core of the gold is a naked to be in the catalytic reaction. We need to study actually the geometry and the structure, because every catalytic activity is different compared with the size and geometry and the structure, as well as the electronic structure. And that's why it's becoming different by counting the atoms of the nanocluster itself. And we need to tune that size of the regime to have their properties, to understand their catalytic activities. This is a project overview. It's involved like 5-6 different universities and institutes, and it's funded by the Australian government and US Army. And it goes through a multiple spectroscopic and microscopic techniques, as well as the application of the photocatalytic activity as well. I will mention not all of them, but some of them, especially about spectroscopy, XPS, and microscopy, STEM and STM-AFM, and also some of the results from the application itself. We need to, as I mentioned before, we need this cluster to be deposited on the method which has a ligand. We either immerse it on the solution, or by the Bell's nozzle, or by evaporation. We're trying a different method of the deposition with the different criteria, and we generate them actually with a different metal. But I will just focus on the gold 9 on this presentation, because this is the core of my research. It has been producing, I mean, the group we work with as a chemist, they're producing even gold 8 and 9 and 11. It's exactly gold 8 and 9 and 11. They measure it and they screen it by NMR, and by also a different mass spectrometer. And what they have, the purification, it's a bit difficult actually for this nanocluster to have it in precise atoms. We deposit them and we remove the ligands, because at the end we need the access to the gold core for the cluster itself, and we use it for the application. We use a different substrate. We use a titania, we use a nano sheet titania B25, which is anatase titan nanoparticles, and we do sometimes a pre-treatment to actually have this cluster attached to the surface and not easy to immobilize. And we do a post-treatment. We heat it, like, for example, 200 degrees to remove the ligands, and we study by the different techniques to have what's happened to the size and to the regime, to the electronic structure of this cluster. Our main goal is having this gold cluster at the end as a naked gold cluster, which is removed by the ligands and is easy access, but without any aggregation of this cluster. This is as it is. We deposit them on the metal oxide and we remove the ligands, and we aim to have this cluster as individual. This is where the unique of the catalytic activities of every precise nanocluster. We use the XPS, and as you know, XPS is used for the chemical elemental peaks, and we can, it's just a photon. We ejecting the electrons and studying and recording the binding energy actually for the photon overcome this kind of binding energy of the electron. But and this is our machine there in Australia. And for the XPS, we have also the MES and UBS. And the MES, we study the outmost layer, which I will not talk about in this presentation for the time. But this is one of the unique techniques where we use a metastable helium to have a very actually ejected electron at the outmost layer. The depth is just a 0 nanometer. It's just on the outmost layer, while the XPS, it can be penetrate to like 2 or 3 nanometers, depend on the electron main path of the metal itself. Because we have a very small nanocluster, sometimes the intensity of this peak on the XPS is not that much. That's why we move to the cyclotron XPS. Cyclotron XPX is a huge radiation that we can narrow actually the energy gap and have a huge intensity to show us this amount, because we deposit a very little amount to avoid the aggregation of the nanocluster. We done a study on the cyclotron, and we show actually there is a huge difference between the gold 8 and 9 and even 11 and gold 101 atoms depend on the actually the peak, and this is what's called the size effect of the XPS, and this is related to the final state effect. What does the final state effect? It's mean that the cluster itself getting actually on the charge state when the photon hits, and it has been a period of time to get a relaxation, and this relaxation is actually a fingerprint of these different cluster. On the peak actually of the gold itself, it's if you're looking for the bulk gold, usually it's 84 electron volt, the binding energy. while we saw a shift actually of this 84 to a higher binding energy, and this is related to the final state effect of every single cluster. Once we get to 86 and above, this is like oxidation, and this is a chemical shift, but we are not reaching the chemical shift, we are reaching the size depending on the XPS, and this is how you interpret it as the different sizes will behave on a different in the XPS itself. And we move to the STEM, scanning transmission electron microscope. First, we deposit them in oxide, as I mentioned, to increase the catalytic activities of our gold nanocluster. We start with the unique titanium sheet, which is special for the NIMS Institute, where we have just a single layer of the nano sheet with a huge wide range, and we deposit our gold cluster. The thickness is just 1.2 nanometer of this sheet exactly. We use the scanning transmission electron microscope, and this is as aberration corrected actually, where we can reach to the atomic resolution. This atomic resolution is depend on the electron beam diameter, which is around 0.1, which is applicable to the imaging of the atom itself. This was in NIMS in Japan. And we can actually show our gold nanocluster depositing on titanium nanosheet. And we classified them to 3 categories. The first category, as you saw here, and what you're measuring now is, what you saw now is the white spot is just the single atom itself. And the scale bar here is 0.5 nanometer, which is related to the gold core of our nanocluster. And we saw them actually as in 3D dimension at the beginning. Then when is it removing some of the ligands because of the attachment to the nano sheet, and because the electron beam, we saw a 2-dimension actually of this nanocluster. This will help us to understand what's the structure and how it looks like our gold 9 cluster when it's deposited on nano sheet. And this is have been actually also, this is another images with the same gold nanocluster, and we have it has been compared actually with the DFT calculation, the density functional theory, where we have this kind of structure. Actually, it's on the lower relative energy. We have it with the ligands, and once they attach the ligands, we have it on the 2D dimension. That's mean when we deposit this gold nanocluster, it has been changing in terms of the deposition. There is one structure, which is the isomer here, we couldn't find because this is actually a transition state, and it's hard actually maybe to visualize by the STEM. As far as you know, this is the lowest number of the gold nanocluster has been seen actually in literature. The record was before us is gold 39, which is the gold cluster has 39 atoms, and visualizing a very small gold, just 9 gold atoms is very hard and very challenging, because you already deposit some energy from the electron beam itself, and this is energized actually cluster, and it's very hard actually to identify this gold nanocluster. We know the world is not perfect, and that's why we get some aggregation already because of the electron beam, but also we get some fragment of this nanocluster where we have like atoms, one single atoms, dimer and trimer of these 3, and these are like just the 3 atoms, and we report them also with the XPS finding. This is the gold 9 cluster. It's exactly what has been reported for our previous papers with using the cyclotron itself. Which means that at the beginning, we have like a 3D structure with the ligands. When is it interact with the surface or any of the ligands removed is changing the structure of this nanocluster. We also deposit them on the B25, which is the titanium nanoparticles. And we can show a different actually before removing the ligands and after removing the ligands. And we saw some aggregation. And this is also the STEM images of The large one is the P25, this one is the gold 9 deposit actually on the top of the P25, which is the titanium nanoparticles. We usually trying to avoid the aggregation as much as we can, because this is not our actually target, and this is a huge challenge in nanoparticles, even in nanoscale, because you will end with a different electronic structure. And there is no actually benefit of being precise on the gold on the nanocluster itself. We need to target a specific regime size to have it doing a specific catalytic reaction in the reaction itself. And to actually measuring this agglomeration, we need such of the scanning probe microscope, like atomic force microscopy and ST and scanning tunneling microscope, to measure the degree of the aggregation when we deposit them on the metal oxide itself. And we deposit them on titanium nanosheet, and we checking before annealing and after annealing. And after annealing, when we remove actually the ligands itself, we remove it at 200 degrees for like 20 minutes, and we be sure we are not actually having any phosphine. And we confirm that by the XPS itself, where we don't have any peaks of the phosphorus after we annealed and remove the ligands itself. And the lateral resolution in AFM is showing the cluster size for our gold 9 nanocluster. And we saw actually quite of aggregation after annealing. And this is related to removing the ligands and giving the nanocluster the organize itself to have to actually have it on the different size. The gold 9 on titanium nanosheet, we saw as a deposit, we have as a deposit, we have around like 1.2 nanometer. This is with the ligands. And when we annealed this gold nanocluster, we show them it's getting a higher on the height. And this is quite of the annealing, and this is the aggregation degree for our gold 9. We use also a scanning tunneling microscope. It's not the easy techniques actually to use, and it's a bit challenging because you are getting the tip itself very close to the sample. It's just on the gap of 1 nanometer. And with any contamination, with any impurities, any kind of damage, you will lose actually the signal. And you also, what we're doing in scanning tunneling microscope, we throw the tunneling as a current. And this is the electrons jumping from the tip itself to the sample by reducing the bias voltage actually from the sample and trying to measure. The difference between the STM and the AFM is looking for the lateral resolution itself and can be working on the ambient condition. But the STM is working in very ultra high vacuum and can be vary in the temperature as well. But we are looking for the electron cloud itself, because it's looking for the electron density itself. It's not anymore looking for the laterals like such the AFM. And this is why it's giving more high resolution by using the STM itself. We have the titanium nanosheet, and this is titanium nanosheet. We measure them as a reference sample before and after annealing to see what kind of changing happened to the substrate before we deposit our gold 9. But once we deposit our gold 9, we saw actually the gold 9 before and after annealing. And this is actually an imaging, a close imaging of a single nanocluster deposit on nanosheet using the STM itself. And we create a histogram from it, and we saw actually the size has been reduction, and this is related to the actually removing of the ligands itself from the nanocluster. And we tried also to using the XPS before and after anneal to show actually the degree of the aggregation. We still have remaining, even after annealing, some isolated gold 9, which being isolated. but we have also the aggregation of gold-9. But for sure, we don't have any phosphorus left, which is mean the ligands is containing the phosphorus itself is detached from the gold-9 nanocluster. We also use atomic layer deposition, which is a very thin of the titania deposit on the substrate with like thickness of 100-120 nanometer. And we study actually this kind of nanocluster aggregation and the degree of aggregation on a different titania oxide. Like we tried the nanosheet and we tried B25, and now we tried the atomic layer deposition. And we spatter this kind, create what's called the oxygen defects. And this is what on the substrate and itself. But even though we have some aggregation of this gold-9 cluster, and this is what's showing on the histogram, because the size is increasing, the tail is increasing actually. And this is like a two different methodology. We have the spatter ALD, we have the titanium sheet, but the aggregation is much stronger actually on the atomic layer deposition. The aggregation degree is much stronger compared with the nanosheet, which we include that nanosheet has more defects, which can hang actually this gold-9 to not be aggregate and can be used for the future for the catalytic reaction itself. For the photocatalyst, the other groups actually in University of Adelaide, they done actually some of the photocatalytic reaction, especially by actually using for the hydrogen production and for the water splitting to producing the hydrogen production. And this is the phenomena actually that we deposit the gold on the top of the oxide surface to increase the catalytic reaction and to have this kind of exchange on the top of the metal core, and to do the reaction of the catalytic reaction by the reduction of the water itself and producing the hydrogen, and also for the reduction of the CO2 emission and to get the methanol itself. And they create actually, our group in Adelaide Uni, they create a reactor which we can perform actually the catalytic reaction itself. And this is a reaction actually can measure a very precise, a different temperature producing by the hydrogen itself, and can measure a very amount actually of the hydrogen production reach to the micromoles for the material itself. Primarily, actual results show that we deposit the gold on the different, as I said, different thing. Actually, they're showing the heat treated of the gold-9 on B25. It's even is getting partial agglomeration, but it's showing actually when we have loss of the ligands and there is no aggregation degree, effective gold-9 deposit on the titania, showing a very nice result of the production of the hydrogen. So very advanced nanomaterials that can be targeting in atoms, not just even in nanomaterials scale, and can have more precise, more fundamentals. There's a huge challenge in keeping and studying these kind of small atoms and manipulating these atoms. But with the more practice, with the more experience, this field, I guess this is a future actually fusing this kind of a precise atoms to avoid any wasting materials, and reusing this kind of materials and knowing exactly by this precise regime how can we produce a very clean energy. This work has lots of contributions from a different university and different institutes. All thanks goes to them. And by this, I will end my presentation and welcoming for any questions.
Thank you very much, Dr. Hassan. Very nice presentations. So I saw in the chat room is already many questions. So I will open now for the question and answers. Okay, Mr. Tiurma, please. Yes, you can ask directly to Dr. Hassan.
Okay, hello, good afternoon, Mr. Hassan. Greetings. My name is Miss Tiurma. I was graduate from Bandung Institute of Technology in chemistry majoring, and then I have only one question, but actually I have a one. So the first one is which one from your method with STEM or whether from what you have explained as the qualitative or the quantitative ones. I'm sorry that I don't get the differences. And then the second one, is it available to the drug discovery research? Okay, thank you for your explanation. I hope that my sounds good hearing clear.
Yes, it's quite
Yeah,
clear.
yeah. Thanks a lot. This is very nice questions. Yes, not all of them is quantitative actually measurement. Like for example, the MEAS, which I didn't discuss, is qualitative measurement, while the XPS is a direct measurement that you can figure out. This cluster, I mean, nanoparticles has been used in drugs delivery and different things. But in our gold 9 actually was, which we has a chemical synthesizer, we're targeting to being as a catalyst. But it hasn't been used for the drug delivery itself.
Okay, that's all, Dr. Hassan?
Yes.
Okay. Okay, so next question is from the MKH in the chat room. Do you foresee any other potential application for such AU9 or so other than photocatalyst?
Yeah, I mean, the gold line itself as without the stabilize the ligands, yet it will be using, for example, for the plasmonic effects, and can be using for the sensing, and other application can be used as well. It's about the way actually we actually synthesize them, and we synthesize them to having these ligands to protection and to make it more stable for the chemical use and for a longer time. But yes, definitely can be used for another application.
Okay, that's good. So, Dr. Hassan, I'm wondering how you make. I mean, how you make the atomic gold move to this side, to this side, to this side. I believe using kind of STM or other thing. Could you explain to us in the how it works, how to you move any kind of that atom to this side, to the other side, and other things. So could you explain to us about that?
Yeah, I mean, to be honest, I mean, synthesizing this kind of precise gold nanocluster is not that easy.
Okay.
And this is our collaboration team on New Zealand in Canterbury University. They synthesize this gold nanocluster. They have published in Nature about this actually synthesis. It's actually getting starting with the huge bulk gold, then trying to reaching to a few atoms, 100 atoms, then getting down to the precise atoms they need. It's need a very involved experience actually on the chemist to have this kind of a precise gold nanocluster. And not even that, having a purified gold nanocluster on the precise size, like 8 or 9 or 11, very, very difficult. And that's why they need multiples of purification. And that's why they need the IC for mass spectroscopy to have exactly this kind of something.
When I was acting with you, you made some kind of flower, right? From the nano gold.
Yeah. Yes, you are right. That
Am I
was
correct?
some part of my.
Looks like a flower. Yeah.
Yes, you are right. And definitely, I mean, a different shape can have a different. Yeah.
So, okay, brothers, I think your presentation is very good and also very nice. It's opened my mind, so you can make cluster of nano gold. AU9 is very small, right? It's I think AU thing is small, so as far as you know, it's the smallest one, right? Until now.
Yeah.
So it's good for us in Indonesia, so we can we know that it's not easy, of course, but you see University of Canterbury and other institutions such as Saudi Aramco and other things.
Yeah.
So you have a closing statement about your presentation and then about your maybe you are open for collaboration with the Indonesian Institute or maybe in Indonesian University, you have other things. Maybe we want to know about that one.
It's actually, I mean, the motivation of my presentation today, it's toward the hydrogen production. And even the kingdom here, I mean, we're starting now one of the largest world actually building hydrogen plant in Neom. And this is with a huge cost of 700 billion. It's a very huge cost actually, and one of the largest plant on the world. I mean, this is the future actually, coming to the clean energy and green energy as well.
Okay. So
And
okay, I
thanks
think
a lot,
it's
guys.
enough. Yeah. Also, we are thanks having you in here. It's
No
good
worries,
for us.
no worries. It's my pleasure.
No worries. Okay, it's also my pleasure.
Thank
so,
you.
okay, I think it's enough for the main session. So I go to the next session. So please, Mr. Fikri, to handle the sessions. Thank you all the participants, also our special guest, Dr. Hasan Al-Fahtani.
Thanks a lot.
Assalamualaikum warahmatullahi wabarakatuh.